So is this visible? Anybody?
Yes, sir, it is visible.
Just check this thing. Is this marking visible?
Yes, sir.
Okay. So let us see this problem today that we have seen briefly yesterday, but I thought of telling you once again this because there was some issue yesterday. So let us solve this problem. Design a linear predictor using following data. So data is, we have my input x1, this is my input x2, and this is my output y. So what I assume here is I have two inputs, that is x1 and x2, outside temperature and persons, number of persons in room. So here onwards, whatever is available is my output. Okay, so y is my output. Now question is, if temperature is 7.5 and say that is degrees Celsius and number of persons in the room are 131, what is energy consumption? This is my question. So this I want to predict. Why I'm saying prediction? Because this entry of 7.5 and 131, this data is not available. So I have to predict this information based on whatever I have in my hand. So this is what is called as regression. You predict something which is not available with you, or the information is missing. So what we do is we take the help of these four samples and try to fit some model. So here my model assumption is y is equal to some theta 0 plus theta 1 x1 plus theta 2 x2. This is my assumption. So this is assumed. Okay, so this is my assumption. Now question is, what are the values of theta 1, theta 2 and theta 0? This I don't know. So we will try to find out these values based on these four available samples. If suppose there are 20 such samples are available, you can take help of all of them. So that is what is called as training data. So this is called as training data. Now what I did is I just took this table, complete table, and I break this or form this uh, y vector, this x matrix, and this is theta. Theta is just collection of the theta variable. So theta 0, say as my model is theta 0 plus theta 1 x1 plus theta 2 x2. This is my model. So this theta 0 will go here, theta 1 is written here, and theta 2 is here. Now from the table, I take all the output values, say this output values, this output values, 0.5, 2.5, 2.2 and 1.8. This I am writing as output. So y is equal to this thing. And x, first of all, for designing x, we know that I should write 1 at the beginning for all the entries. So this is the entry of the multiplicand of this theta 0. Okay, so this multiplicand of theta 0 is 1, so I am writing here 1. Then I write the entries for respective sample. So this 10 2, then 542, then I will write 4.5, 31 and 6 and 35. This will be written as entries over here. So this is 10 2, this is first sample, this is 542 is second sample, 4.531 is third sample, 6 and 35 is fourth sample. Suppose there is a fifth sample, then you will add 1 here and then you will write fifth sample and so on. So that will be your procedure. Okay. Now we have only one step to compute theta. It's very simple to calculate theta. We have to implement only this equation. What we have to do is we have to take the X matrix, then we have to transpose it, then you have to multiply with X. Then you take this complete multiplication and find out inverse of that. Okay, once that is done, you will take another X transpose Y and you will multiply with this bracket. Once you do that, immediately you will get three values like this. So theta vector will be like this. So here this first entry is theta 0, the second entry is theta 1, and third entry is theta 2. So you will see a small program for this. So I will be providing you this code. You have to modify this code as per the requirement given in the problem. So let us import first NumPy. So NumPy is imported. Then I create an array of the y. So this is array of y. So all entries of y, that is this entries, you can see this 0.5, 2.5, 2.2 and 1.8, these are written here. Okay, so this is my y vector. Okay, this is my y vector. Then I define that matrix X where I should have this entries like this, say 1 1 1 should be here, and this data should form matrix X. So this is matrix X. That is what is defined here. So this is my matrix X. Okay. So if I print it, it will be looking like this. I hope there is no doubt here. Is this fine?
Yes, sir.
Okay. Now let us first of all do this thing. X transpose X inverse. Okay, so there are three operations. First of all, I need to transpose this X, then multiply with X, and then take inverse. So you can do this in one go in Python. So first of all, we will do this X transpose X inverse. So the command is dot inverse, and then np.matmul will give you matrix multiplication, and transpose X dot transpose will give you X transpose. So this will be X transpose multiplied with X. So this will be this operation, and dot inverse will give you this inverse. So this is done here. In one line you can do this. Okay. So if you print this, it will be looking like this. Next step is to multiply X transpose Y. So we will compute X transpose Y first. We take that X and write here X transpose. So this will give you X transpose multiplied by Y. So this matmul function, np.matmul function will do this. Okay, so once you have X transpose Y here and X transpose X inverse here, next step is to multiply these two. Okay, so that will give you directly theta. So I call this multiplication as theta. There I just do this matrix multiplication of X transpose X inverse and X transpose Y. So here I am implementing this equation. Okay, so in one step you will see that I get three values of theta. So first value is theta 0, second value is theta 1, and third value is theta 2. Now this model is ready. I want to use for calculating the answer. Like my question, if you remember, was if temperature is 7.5 degrees Celsius, number of people in room are 131, what is energy consumption? This I want to predict. Okay, this is my prediction. So what I do, I take a variable 7.5 as temperature. I take this number of people as numpy 131, and then I implement this equation. And what is this equation? If you see carefully, I am just doing this. Y is equal to theta 0 plus theta 1, okay, into x1 plus theta 2 into x2. Now what is x1 here? It is the first variable. So I write here temperature. That was my first variable in that table. And the second variable is number of persons or people. Okay, so number of people is my second variable. So I just implement this. Now I know theta values. So theta 0, theta 1, theta 2 is known to me. So you can check here this first number 2.4, 2.49 and so on is the first number in this particular theta 0 vector. So this first number is substituted here as theta 0. The second number you can see here is written over here as theta 1. Then I write this multiplied by the first variable, that is temperature. Then I take third component, this one, then it will go here. Okay, so this will be my theta 2 and multiplied by x2. Okay, so same thing is written here. So what I do now, I just substitute values of 7.5 and 131 into this equation. Directly it will predict the energy consumption as 3.6, which looks quite good kind of prediction. So if you see the table, so last entry is, suppose here is 7.5 and 131. So it is giving you, I think, 3.8. So it looks pretty good. So you can just implement this code for yourself, and then you put any value. So maybe you can put here some temperature as 6.5 and maybe 52 people, then what is value. So you can easily predict. Okay, so this is a very good example to tell you what exactly is regression. Remember, you can add many variables here. So this is x1, x2 here. You can add maybe x3, x4, and so on up to maybe x20 and so. Okay, so this is quite possible. And then you can predict some variable, so or a dependent variable. Any doubt here? I can proceed further.
Yes,
Shall
sir.
I move on? Okay. Now the next part is, you can note down this as linear regression using gradient descent. Okay, so this is based on some principle of gradient of a scalar. Okay, so what is that? We will see now. So gradient of a scalar or a gradient vector is obtained by differentiating a scalar quantity or a function with respect to different variables. Okay, for example, f is a function, f is a function of many variables, say x1, x2 up to say xn. Then I can differentiate this f with respect to x1. I can differentiate this f with respect to x2, and so on. I can differentiate with respect to xn. And this differentiation, if I collect and place like this, it is called as gradient vector. So gradient vector is nothing but just a collection of differentiation with respect to different variables for a function. Now, the physical significance of this you will come to know if I take this example. Suppose this is a mountain, and you know that this is my height of a mountain. Okay, and let us say this is your position or coordinate of that particular point. So I can say this is x or x1, and this side I can say y. Okay, and this height is like this. So suppose I stand here, and the coordinates are, let us say, y is some 5 and x is say 10, then point becomes 10 5, and corresponding height is suppose 50 meters. Okay, so this point, this height at this point, say p1, is equal to 50 meters, and this height is a function of x and y. So if you change value of this x and y, you will get different values of height. Okay, so you can take this top view instead of the side view, then I think it will be more better. So this side is now I can call as suppose y, and this side is x, and height of this is, if you can see or visualize, the third axis which we are looking from now top. So this is the peak point of this mountain, and this is the ground of this mountain or ground point. Okay, and the mountain, the height is a function like this. Okay, and maybe if you are standing here, it will be like this. Now when I take gradient of this, so you can see here equi-heighted points or locus of equi-heighted points. So this is the ground point, and this is the max point, highest point, or a max point. This is the max point, and this is ground point. Okay, and if I stand suppose here and take gradient of height, you can compute here in this case by differentiating this height quantity or a height function with respect to x and with respect to y. If you place this thing in a vector, this will be called as gradient of height. Okay, so and this vector is pointing always towards maxima of the function. So this you note down. A gradient of a scalar function always point towards the maxima of that function. So if you stand over here and take gradient of height for this particular position, it will point towards this maxima. So suppose you stand over here and take gradient at that point, it will point towards this maxima. Similarly, if you stand here, then it will point towards this. If you stand here, it will show towards this. So it is always showing you a path where that particular function maximizes. Okay, that particular function gets maximized. So if you stand in this valley, say if you stand over here, then you will be pointed towards maxima of this valley. Okay, so if you stand over here, you will be pointed towards maxima. Now inspired from this, what we do is we assume that this is the error surface. This is the error surface. So this is the error surface, and we want to minimize error. What is my error? As you have seen earlier, the error was the y actual value minus y, the predicted value difference and square of that. So multiplied by half. So this was my error in prediction. So this we have defined earlier. Now, if I take gradient of error, then suppose these are the, you can say I'm standing over here and I take gradient of error. Now I call this mountain as error mountain. Okay, then I am shown this path that is towards maxima. But I want to travel towards minima. I don't want to maximize the error, I want to minimize the error. So what I do, I take negative of the gradient. So if I take negative of the gradient, I will be thrown towards minima of the value. Okay, I always want to travel towards minima, not maxima. So we are interested actually in negative gradient of error. So we will walk on the mountain such that our error is minimized, not maximized. So the direction is negative gradient of error. So this is a very simple idea, and we will see now how we can implement this idea. Now what we are trying to do here is, since in your earlier problem where we obtained theta, which was in terms of x like this, x transpose x inverse, I think x transpose y. This was calculating your theta directly in one step. But what is problem over here is this quantity must be invertible, that is x transpose x inverse, it should exist, otherwise this method will fail. Okay, now we cannot assure that given data will follow this property. Okay, so to do in such situation, instead of doing like this, and if suppose x is of 100 dimension, then this 100 dimension by 100 dimension, then inverse of this, so it will be a very computationally intensive kind of a thing. Maybe you have 1,000 samples, then it will be 1,000 by 1,000, 1,000 by 1,000 matrix. You can imagine inverse of that. So how much computational energy will be required to do this? You may have 10,000 samples, then this will grow like anything. So computational complexity is very high when data points are quite high. So instead of that, we are now using a new method called as gradient descent method. This is most popular method in machine learning and neural networks. Hello. Okay. Now what we do, just see here. Let us define the error, which is as usual like this, where yi is just the actual value of ith sample and yi hat is prediction. Okay. Now I differentiate with theta j. Theta j is my variable associated with that error. Okay, so here y hat, I assume it is as usual theta 0 plus theta 1 x1 plus theta 2 x2 and so on up to, let us say, theta d xd. Okay, so if you differentiate with respect to theta j, I can add here some theta j if you want. So this will be some theta j xj, some intermediate theta. So I take just theta j as to represent all these thetas. So you have to repeat this differentiation for all thetas, that is j equal to 0 to d. Okay. Now if you differentiate this term with respect to theta j, Since y hat is of this form, you can easily differentiate. So I just substitute here this y cap value like this, as it is stated earlier. This is nothing but y cap. So this is nothing but y cap. Now if you differentiate with respect to theta j, only term associated with is this. So all other differentiations will be 0. And when you differentiate this term with respect to theta j, only xij will be remaining. So let's do that. So this is my outcome due to differentiation with respect to theta j. Okay, so that is d, this should be y, this should be yi minus y cap, okay, into xij minus, okay, this should be correction here. So this is gradient with respect to theta j. Now you have to do this for all, that is theta 0 to theta d, then you will get the gradient vector, say gradient vector e theta. But what we want is negative of this. This is important. I want negative of this gradient, not the positive. Because if you consider positive, this will be showing you a path to maxima. If you take a negative, then it will be showing you path of minima. And we want to minimize error, not maximize. So we take negative of this. So once you take negative of this, this will be your total gradient vector, negative gradient vector. Now what I do is I travel or change values of theta in the negative gradient direction. What I mean to say is we will first of all randomly assume, since I don't know solution of my problem, I randomly assume theta vector and just I calculate based on this randomly assumed solution some error. Once I compute that error, I know that if it is more than the required or satisfactory error, then I have to update theta. Okay, so how do I update theta? So theta new is equal to theta old plus delta theta. This is the thing I am going to do. Now delta theta, the little step, say for example this is my x and this is say y, or I should write x1 and x2, and this is my error, and let us assume some surface like this for error. Some kind of a surface like this. Say when you randomly assume some value of theta, let us say this is the position where you are standing right now. So this I should take better is theta 1 and theta 2 because that are the variables, not x1, x2. Say you are standing with this initial random guess, then this is theta 2 and this will be your theta 1. Okay, and with this you obtain this much error. So this is your error. Now you want to travel towards this minima. So this minima is here. So you take here gradient of error, negative gradient of error, and this will push you towards this minima. So you can travel in this direction maybe up to this point. So how much you will travel? If you travel with this big step, you will miss this minima. Okay, so you will be thrown away to a point where actual error is more. So you are standing, suppose here, then error is more. So what you do is you take a small step. You take a small step in that direction. So you are standing here, then you will reach here. Okay, so you are standing here, then you will go to next step with a baby step. Okay, now how you control that step is by controlling or giving a parameter called as learning constant. So maybe you choose a small learning constant. You will be traveling in proper direction, but in a small step. So I will give you a program which will tell you all this. So once you do this for repeatedly for all training samples, you will travel from this point and go to this point. That is minimum possible error. So once you reach this point, that is the fittest point for a given problem. And based on this theta, whatever you design, the model will be the best possible model for the given data. Then you can start using this theta for prediction. So I will tell you how you can do this. The algorithm is like this. First of all, randomly initialize theta. You can assume any value for this theta. Maybe suppose for our earlier problem, I can start with, say, let us say 0.1, 0.4 or whatever I feel. I just assume randomly this is my solution. This is my randomly guess solution. Then I assume some Emax that I allow. So I say that squared error cannot be more than 0.05. Okay, that is my assumption. You can set your own value. Maybe you can set 0.001. I want more, you can say, accurate system. Then repeat for all training samples the following loop. So you can set the count. Maybe I will do this at the most 10,000 times, because you may not achieve Emax in finite time. You may have to repeat and your computer may get hanged. So you have to put this maximum count that I will do this for 10,000 times. Okay, and then you will start the actual program. Now what this program is doing is it is initializing the error in the loop equal to 0 with the given theta. Assume theta here. You estimate y for a given sample. Say sample number 1 is taken, and then you will calculate predicted value for that. And if this E is more than E max, then you will compute this change in theta. So change in theta is eta, that is learning constant, into this difference, that is the actual value required and estimated, multiplied by input. Okay, so this formula we have obtained from last derivation. Then you update this theta new is equal to theta old plus delta theta. Let us see with one example how we can do this. You can ask me in between if you have any doubt. So let us say I have only very simple program. This is only one variable. You can have many variables. You can solve for many variables. See, this is only single input and single output. So this was the first data that we have seen for regression, where we could fit a straight line. So this program will fit a straight line. Now see here, the function is gradient descent function that I am writing. So let us say take this loop variable equal to 0. Say learning constant is 0.01, and then I assume theta. Say theta here is, say, beta 0 and beta 1, this is equal to 0.2 and this is 0.4. That is a random guess for my this data. I don't know what kind of line is good for me. I can put any number here, that is allowed. Then I put Emax is equal to 0.01. Okay, that is maximum error allowed by me. You can put anything here. Let us start with equal to 0, and then we will be in a loop which will be repeated for 10,000 times. Now we start from I equal to 1 to the length of x. That is, this is in case of Python, it will be I equal to 0 to 1, 2, 3, 4, 5. That means it will run up to 4. Okay, so this I will be from 0 to 4, that is 5 numbers. So one by one we will take the input from the table, and then we will calculate here y cap for each input, and we will compare with corresponding y. Okay, so we will estimate one by one all values, and then we will compare. So the comparison will be here. So error is computed here. So y will be, suppose I equal to 0. So first number is taken from the table, and then it will be compared with estimated value. How you estimate? This equation will do the estimation. What it is implementing? It is implementing, say, beta 0 plus beta 1 x. So y cap is equal to beta 0 plus beta 1 x. So this is a linear model, simple linear model fitting a straight line. Then if your error is more than permissible error. So what is permissible error? Permissible error is 0.01. If it is more than that, it will adjust this theta vector. So we have two parameters right now, beta 0 and beta 1, that you can directly change using derived formula. Derived formula is this: change in theta is equal to learning constant multiplied by y minus y cap into x. So that is what is implemented here. Since here x is always 1, so I need not write here for beta 0. Beta 0 has no x variable, so it will be always multiplied by 1. So if you run this program, see what happens. So initially we will, that was my function which implements actual algorithm, and this is my data. So this table is made here. Then I take the rows of, say, columns of this table and put it as x and y. So these two lines will separate x and y. Then you can plot them. So these are 5 samples plotted over here, and then you call your earlier program. This was given to you earlier. So this is the old program that is called over here to directly compute this best fit line using minimum squared error algorithm. So that will give you directly this beta equal to 0.4 and 0.8. So this was given to you earlier. So this is old program which directly calculates beta based on this data. Now the second program, which is based on gradient descent, is called over here. Now if you run this with this data provided, you will see that the estimation is very close to the actual value. Okay, this is run with random guess. See the difference between two methods. I randomly guess theta here, and then I run my algorithm through the training data samples one by one, and then I adjust theta. So theta is always adjusted so that error is minimized. And in the first method, I take the help of all samples at a time and I compute directly values of theta. Okay, so this is possible with the first method. In second method, I randomly assume theta and then I settle to a proper value of theta. But this second method is very advantageous over the first one when number of variables are more. Suppose I have say 50 variables, my output y depends on 50 variables. Then to find out beta 0, beta 1, beta 2 and so on up to beta 50, it's very difficult. Okay, we cannot solve like keep on solving like this. So instead of that, what we do, we take this theta and randomly assume 50 values for that. Okay, we just put random 50 values here and then try to adjust this theta by presenting one by one all the samples to the system. If system produces error, adjust this theta. If it is not producing error, leave it. Okay, so you keep on doing changes in your theta such that you will land to a solution. So you will get a best fit line over here. So try to understand this concept. If you have any doubt, you can ask me in next class. I will give you this code maybe today or maybe tomorrow morning, right? So let us stop here.